Okay, so good afternoon to all the participants. So now this is the second day of third session. So now in this session that we will discuss this CNN, convolution neural network. So before start this convolution neural network, so first let us understand the difference between the neural network, or in fact I should say the artificial neural network and the CNN. So in artificial neural network, that uh, we are dealing with the matrix multiplication. Okay, so that I will explain in detail this difference. So here in ANN, we are dealing with the matrix multiplication, and here in CNN, that is convolution operation is performed. Convolution operation is performed. Okay, so this is a kind of the basic difference, and there are certain issues, the problem that encounter in the artificial neural network, okay, that we can solve through this CNN, convolution neural network. Wait, let me check the chat box. Sorry, actually I forgot to ask you, is my voice and this PPT is visible to all of you?
Yes, sir. Yes, sir. It is clear, sir.
Oh, okay, okay, thank you, sir. Okay, fine. So voice is low. Okay, wait. Okay, so now is it fine? Okay, okay, good. Okay, so now another difference between this ANN, the way of this providing the input in ANN and CNN, that is entirely different. So in ANN, artificial neural network, that we give input in a one-dimensional way, and in this CNN, that is this CNN is actually is the best suited for the image type of data set. Okay, so there's a image. Okay, and basically I should say it's a grid-like topology. Grid-like topology. The grid-like topology. So grid-like topology means that is a kind of time series data. So it may be the one-dimensional data or it's a 2D data. Okay. So the image that is as a 2D. This one is a 2D. Okay. So this one dimension and two dimension, this image that is best suited for this CNN kind of this model, where this ANN that we provide that the input in a one dimensional way. So okay, one dimension. So first we have to just convert this. If suppose if I am comparing this ANN to this CNN, so this one is the image. Okay, and how do we give the input to the artificial neural network? So this one is a one first row. Okay, now the second row, this one is the second row, this one is a kind of third row. Okay, so let's say my dimension of this image is 784 multiplied by 784, or maybe more than this one. So now the 784 cross 784. Now you see this. If you give the input to this ANN, the computation cost is very high. Okay, so that is a one kind of the issue, or you can say is a kind of the drawback. In this computation cost is very high in this artificial neural network. So that is a first. So that is a first problem, is that is a computation cost that is very high. Okay. So second problem is that is overfitting. So second problem is that is overfitting. Overfitting means uh, that is low bias and high variance. Low bias and high variance. That is the overfitting. Or you can say the overfitting. My model that work very fine, very well on the training data set. The moment that I change the data, that it may not perform as well as on the training data. Okay, so that is overfitting. So that is a kind of second issue, that is second problem that I encounter in this artificial neural network. And the third issue is there is a loss of information. It's a loss of information. Okay, that is a spatial arrangement of pixel. Okay, that I can say this spatial arrangement of pixel. So spatial arrangement of pixel is, let's say this one is a human being. Okay, and this one is a kind of this eyes, and this one is a nose. So there is a distance between this, between convert this in a one dimension. Okay, so now the spatial arrangement of a pixel now it is disturbed. It is getting disturbed when you convert this image in a one dimension. There is a means it take lot of time to train the data. Okay, and the model loss information of spatial arrangement of pixel. Okay. So now in this one, we can understand the CNN and the CNN. So there is a one kind of similarity, that is this is the input layer, this one is the hidden layer. Okay, here that is input layer, hidden layer, and the output layer. So input layer, this one is a hidden layer and the output layer. Okay, so in the CNN, so this kind of small similarity is there in between this ANN and CNN. So in this CNN, there are three layers. So in place of this input layer, okay, that is a convolution layer. Second, that is a pooling layer, and third one is a dense layer or fully connected layer. Clear? So this convolution layer is responsible to extract the features from the input data set. Correct? And I will explain in detail of this convolution layer. Now, the second layer is the pooling layer. The pooling layer is just to reduce the dimension of the feature map. And the third one, that is a dense or fully connected layer. And this dense layer or fully connected layer, that is responsible for the classification of the data set. Okay, clear? So here three layer. First one is a convolution layer, second is a pooling layer, and third one that is a dense layer. So this is the architecture of this convolution neural network. And this one is the architecture of this artificial neural network, where the input layer, hidden layer, may be more than one or two hidden layer, and number of neurons that are not fixed. Output layer, okay, in this one, that is the number of neurons, that is again that is not fixed. It depends on the application to application. So likewise here to CNN, there are three different layers. Okay, so convolution layer. So first let us understand the convolution. So here in the in this convolution layer, there is an input image. This one is the input image. That is this one. This one is the input image. Okay, and one kernel. Okay, or you can say there is a one filter or kernel. So this filter or kernel, that is, this filter is analogous to the weights. Okay, and weight or filter, okay, that both are the same. Okay, so you need to update the value of this pixel of the filter ev- at every epoch, or at the time of the at the back propagation. Okay, so this one input image, this one is a filter, and this is a convolution. So now the point is, how do we do this convolution operation? Okay, so the convolution just is very simple. We drag this filter or kernel over to this input image from left to right and top to bottom. Clear? Now the operation is this one. This is the convolution layer. So this one is the input image. Let's say input image is that is n cross n. Okay, or say 5 cross 5. This one is a filter or the kernel. Okay, the dimension, that is 3 cross 3. Clear? And this input image is a grayscale image, that is a value that is in between 0 to 255. And this one, that is output, that we call as a feature map. This one is the input image, this one is a filter, and this is the feature map. And this one, calculation of the dimension of the feature map. So n minus f is equal to n, where n is the dimension of the input image, f, that is the dimension of this filter, n minus f is equal to 1. So this will come equals 3. Now the operation of the filter, sorry, convolution is, now see this. The operation is, we have to add this filter or kernel over to this image from left to right. Okay, so if we drag this filter over to this image from left to right, the first operation is, so now first the filter that first we superimpose on this image. So now this kind of multiplication that will be there, 2 cross 1, 2 multiplied by 1, 5 multiplied by 1, 7 multiplied by 0, 3 multiplied by 1, 2 multiplied by 3, 2 multiplied by 2, and so on. Correct. And the addition of all this multiplication, let's say that is x. So this is the x value. Correct. Now, second time that we uh, scroll this filter over to this image, one pixel to the right. Now 570, 225, and 122. Okay, and again just we have to do the same this process, to follow the same process. 5 multiply by 1, 7 multiply by 1, 0 multiply by this 0, likewise. Okay, and if we add all the multiplication, then the y value, let's say the y value that will be there. So this is the second value of this feature map, and likewise that this one is clear. And the dimension of the feature map is n minus f plus 1 cross n minus f plus 1. So is it okay for you, this convolution operation? Okay, so now you see the this benefit of this convolution. So this convolution, as I said, this convolution operation, convolution layer is mainly responsible to extract the feature from the input image. Okay, so this one, let's say this one is a image of one car, and this is a filter, or this is a kernel. Okay, and this one is the first layer. In fact, this is a first convolution layer. Okay, so now the feature map that maybe look like this one, means it extracts the features. How is the filter dimension decided? So see, the dimension of the this filter, okay, um, is again this application to application, that is not fixed 3 cross 3. Okay, you can take this 5 cross 5. Okay, but maximum that the dimension of the filter, that is maximum 7 cross 7. So I have never seen the dimension more than the 7 cross 7. Okay, so 3 cross 3 or so 5 cross 5, and again it's up to the it depends on the application to application. Okay, so just first you check with the this 3 cross 3. Okay, and again if this feature extraction that is not so accurate, then you may increase the dimension of the filter. Okay, so the second, this one is the second layer, this one is the second layer, this one is the third layer, obviously it's a convolution layer. Okay, now the the feature map, the sorry, the feature, this extraction, feature extraction, that maybe like this one in the, and after this third layer, like this one maybe. Okay, then this one is a fourth layer. Now this one, the feature map, that will be, that is a kind of image of car. Okay, okay, so now this one is very important. Now in place of the grayscale image, so let's take the RGB. Okay, red, green and blue, there's a 3 channel. So let's say the dimension is 6 cross 6. Okay, and this third one, that is a channel. Okay, so RGB. Now this one is a, let me, this one. Okay. Yes. Okay. So this one is a 6 cross 6 cross 3. That is a third dimension of this input image, is a channel, and this one is a filter, the 3 cross 3. Okay. So now important point is here, the third dimension of the filter, that must be the same of the third dimension of this input image. Then only we can do the convolution operation. So this 3 cross 3 cross 3. Okay. So now you tell me the dimension of the feature map. This one is a feature map. Okay. Now you tell me the dimension of the feature map. Okay. So that is n minus my f plus my 1. So that is 6 minus my 3 plus my 1. So that is 4. Okay. So now it's a 4 cross 4. Now tell me the third dimension. This is a 4 cross 4 cross 1. Okay. So the four, not 4 cross 4 cross 3. So the dimension of the feature map, that will be 4 cross 4 cross 1. Okay. So now I'm going to explain this third dimension, that is a 1. Okay. Now you see here, this RGB, that is a 6 cross 6 cross 6. Okay. So this one is the R. Okay. This one is a red channel. Clear? This one is a 6. Now this one is a filter, 3 cross 3. If you convolve this red with this filter, okay, now see, there are 9 multiplication that would be there. Yes or no? You need to multiply this to this to this, and here. Okay, so likewise 9 multiplication and 9 multiplication for this green for with this second channel of the filter, correct, and 9 multiplication of this blue channel with the third channel of this filter. Okay, so that is the so that is would be coming out after the this summation of this filter with this blue channel, 9 multiplication with this one and 9 multiplication with this one. Okay, so now total that multiplication this blue channel. If you add all this 27 multiplication, this value, let's say the value of this 27 multiplication, let's say this value is x. Okay, and the second again, just you shift this filter, okay, to the right of 1 pixel, okay, over to this image, then the value that will be y, then z. Okay, clear? So now the dimension of the filter, that would be 4 cross 4 cross 1, only single channel, only single channel. Siddhant, okay, fine. So are you getting this fine? This RGB, okay, and this 6 cross 6 cross 3, now it's a 3 cross 3 cross 3, and output the dimension of the feature map, that would be 4 cross 4 cross 1, because the number of filter is one filter that has a dimension 3 cross 3 cross 3. Is it okay? Fine. So now this is all about the convolution operation. Okay, so now in this convolution operation there is a one issue. See, the dimension of the this input image is 6 cross 6. There is 3 channel, it's okay. Now the dimension is explain 4 cross 4 using one more piece. Okay, so 4 cross 4, that is coming out from this formula, that is n minus में f plus m1. So n is the dimension of the input image, f that is the dimension of this filter, and plus 1. So 6 minus में 3 plus m1. So again n minus में f plus m1 cross n minus में f plus m1. So that is 4 cross. And the third dimension, that is a single, that is single filter, only one filter. Okay, so that is the reason of this one, that is the third dimension of the feature. If the number of filter that is 2, if number of filter that is 100, if number of filter let's say 200, then accordingly the third dimension of the feature map that will change. Okay, so intuition is movement of filter is overlapping position. Yes, yes. So see, let me explain one more time. So let's say this one is 4 cross 4. This one is a 4 cross. Okay, and filter is this one. This is the convolution operation, and this is 3 cross 3. Okay. So now first you superimpose this filter or to this image, input image. Okay, now here. Now second time here. Okay, third time here, and fourth time this here. Clear? Okay. So that is, and again that is formula that will remain same. So n minus my f plus 1. So now you see here there is a one issue. the output, the dimension of the feature map that should remain same of this input dimension. So input dimension that is 6 cross 6. So the dimension of this feature map that should be 6 cross 6. Okay. Otherwise, some of the information that will lose. Okay. So now for this one, we use the padding. Okay. So if we don't use the padding, now you see the effect. Now this one is the input image 6 cross 6. This one is the filter. Okay, without padding, so the dimension of the feature map that will be 4 cross 4. Now the second filter, second convolution, that is 3 cross 3. Okay, according to the formula, that is n minus f plus m1, that is 2 cross 2. Again, that is filter, that is 3 cross 3. So now output that will not generate. Clear? So that is the benefit of the padding. So see, the one important that misconception is here, that in this padding, the use of padding. Okay, so you see, uh, padding is not doing the dimension of the feature map same with this input image. Let me explain this with the example. So let's say this one is the dimension of the input image, let's say 10 cross 10. Okay, and filter size, that is a 5 cross 5. Okay, the dimension of this feature map after this padding, the formula that will be n minus my f plus my 2p plus 1. N minus my f plus my 2p plus my 1. That is a padding. So there are two types of padding. The first one is a valid, second is the same. So valid means that is a without padding, and same, that is a with padding. Okay, and here this with padding, there are again two types, that is a zero padding, the zero padding that we use for the edge detection. Okay, so zero padding, this is a zero padding, this one is a zero padding. So now here I intentionally put this 0, okay, around this input image. Okay, so now my formula that will this change. So now in place of this n minus f plus m1 before padding, so that is n minus my f plus m1, that is a before padding. Now after padding, so the formula that will be n minus my f plus my 2p plus m1 cross n minus my f plus my 2p plus m1. Clear? So now see, this one is the dimension of the input image, and 3 cross 3, that is a filter. So that is zero padding. So with this zero padding, 5 minus my 3 plus my 2 plus my 1. So the dimension that will be 5 cross 5. Clear? So the padding is useful just to retain the information of the input image. That's it. Okay, so I repeat, just to retain the information, the same information, the whole information. Okay, just to retain the whole information of this input image to the feature map, we use the padding. Okay, so the padding that is padding is not make this dimension of the feature map equal to the dimension of the input image. So now input image, let's say input image that is 10 cross 10. Okay, now 5 cross 5 filter size. Now you tell me the dimension of the feature map with padding. So 10 cross 10 input image, 5 cross 5 filter dimension with padding, the dimension of the feature map. So as per this formula, n minus my f plus my 2p plus my 1. So n is 10 minus my 5 plus my 2 plus my 1. So that is 8. So 8 cross 8. Clear? So input is 10 cross 10. Output 8 cross 8. So padding does not make the dimension of the feature map equal to the dimension of the input image. So padding is useful only just to retain the complete information of the input image to the feature map. Okay, it transfers the whole information from this input to this output or feature map. And there are two types of padding. There is a zero padding and that is same. Okay, valid means that is a without padding. So these two keywords that you will use at the time of the coding. Valid means that is a without padding and same that is a with padding. So I hope it is clear to all of you. Fine. So the next concept is that is stride. Okay, so this is the formula of the stride. Okay, this is after using the stride, n minus में f plus में 2p divided by s plus में 1 cross n minus में f plus में 2p divided by s plus में 1. Okay, so the same means that is a with padding and valid that is a without padding. Okay, so the meaning of the stride is this. Let's say here I am writing 2 comma 2. So what does it mean? So there is a movement of a pixel. Okay, so there is a jump of a pixel. Uh, there is a jump of a 2 pixel to the right. Okay, and there will be a jump of 2 pixel to the bottom side. So the movement of the filter over to this image when we while this convolution operation. So this one is a stride. Let me just explain through one example. So this one is let's say 5 cross 5. This one is a 5 cross 5. Now filter size that is a 3 cross 3. Now first you have to superimpose this filter over to this image like this one. Then second like this one. Then third like this one. And the fourth like this one. Clear? So now as per the formula that is n minus my f plus my 2p divided by s plus my 1. So the benefit of the stride is just to capture the high level feature. Okay, and if you are working on the big data set, okay, now the training time that will be less. Okay, see, the use of the stride or the benefit of the stride is just to capture the high level feature, and the training time that will be less if you are working on the big data set. So let's say the big data set, let's say the input image that is a 8K cross 8K. Okay, and this one is a filter that is a 3 cross 3. So it take lot of time to this train a model. Okay, so now this one is a kind of, let's say this image that is the Indian flag. Okay, so this first row that is a same color, that all the pixel value have the same, all the pixels that are having the same value. In the second row that all the pixels are again are having the same value. In the third row that is again that is all the pixels that are having the this same value. Correct? So better to use the stride. Okay, in that way just you decrease the training time. I hope this is clear to all of you. This stride and this padding. So this stride and padding that is coming under this convolution layer. Okay, now the second one is the polling. Okay, so see there is a one issue in the feature map. Okay, after this convolution layer, the problem is, see, this one, let's say this one is the RGB maze that are having the dimension 220 cross 228 cross 3, and this one is a filter 3 cross 3. Okay, so now the output that will be 228 cross 228, and the number of filter that is 100. So that is the reason of this third dimension of the feature map, that is to be 100. So 228 cross 228 cross 100. Clear? So this one is a feature map with padding. This one is the dimension of the feature map with padding. Clear? And if we use a 32-bit to represent this number, so now the complete, this one is a 228 cross 228 cross 100, 100 cross 32. Clear? So that is, this is having the very large number. Okay, the storage. So just we need to reduce the dimension of the feature map. We need to reduce the dimension of the feature map. So this pooling layer that is responsible for reducing the dimension of the feature map. So now see here. So there, this one is a type of the this pooling. So there's a max pooling, mean pooling, average pooling. So global max and global average. So max pooling, okay. So that is pooling. That is a way of doing the down sample. So see here, the filter size equal to 2, okay, and stride is equal to 2. So I should say the filter is equal to 2 in place of this filter. I should say the window of this size of the window is equal to 2 cross 2, okay, and stride is equal to 2. So that max pooling, okay. So the maximum that pixel value that I have to extract at this max pooling. So 5, 9, 89. Let's say this one is a feature map. This one is a feature map. Okay, and 4 cross 4 dimension. So the dimension after this pooling, the dimension that will be 2 cross 2. Okay, this one is a max pooling. So max pooling, that is 89. Why this 89? Because this is the maximum number. Okay, in this window, that is maximum number is 100. In this window, that is maximum number is 43, and in this window, that is maximum number is 89, and stride is 2. So mean pooling, you have to just pick the minimum value in this window. You have to pick the minimum value from this window, that is a 10, minimum value that is 1, and minimum value that is 34. Average pooling, okay. So just you add all the pixel value and divide by number of the pixel. Divide by number of the pixel. Global max or global average pooling. So this global max pooling, just it convert the whole image in a single scalar value. So better to use this global max pooling or global average pooling at the output side. Okay. So max pooling, this mean pooling, this average pooling, that is fine. But this global max pooling or this global average pooling, just this global max pooling. So let's say this one is a global max pooling. So now maximum value, okay, in this whole image, that maximum value that is 100. So now it convert this image that is 2D in a one scalar value. Okay, and global average pooling. So in this, just you add all the value of this pixel, okay, in this image, and just divide the number of the pixel. That is a global average pooling. Again, that it will be one scalar. Okay, and the last one, that is this is a dense layer, or that is fully connected layer. So this one is a convolution operation. Okay, this one is a pooling. Okay, pooling layer. Okay, this one is a feature map. That is a max pooling. So that is the output after this pooling. Okay, now dense layer. So we need to convert this output in a one dimension. Oh, okay, so this one is a kind of, that is a fully connected. This one is a fully connected layer. Clear? Okay. So now the important point is learnable parameter or trainable parameter. So how do you calculate the learnable parameter? Okay. So now see, in the ANN, this one is a, let's say this one is the input layer. This one is the input layer and this is the hidden layer. So number of weights, that will be 5 cross 3. So 15. Yes. Is there any risk of data loss in pooling? No, actually see, pooling is just to reduce the dimension of the feature map. Okay, and the benefit of this polling is, means the information that will not lose at the this output image. Okay, at the output side, if you don't do polling, if you don't do the polling, the storage that will be, that computation cost, that is very high. Okay. Okay, so now the learnable or trainable parameter. So learnable parameter, that is here in the ANN, that is 5 cross 3, that is a 15. So now these are the weight. Okay, the filter, that pixel value, that is, these are the weight. Clear? So now in the RGB, let's say this one is the RGB image, and this is the filter. So let's say 3 cross 3. Okay, so now tell me how many number of trainable parameter that would be there in this convolution part. This one is, let's say, 6 cross 6 cross 3. So number of trainable parameter, number of trainable parameter, learnable parameter. So number of trainable parameter or learnable parameter, that would be 3 cross 3 cross 3. That is 27. Clear? Okay. So now see, when the number of filter is 50 and input image, that is 5 cross 5 cross 3. Clear? So there's a one filter and this one is a feature map. Okay. Let me just move this feature map. Now you tell me the dimension of the feature map. First you tell me the dimension of, so see, yes, third dimension, 3 cross 3 cross 50. 3 cross 3 cross 50. Okay. So now tell me the number of trainable parameter or learnable parameter. not 3 cross 3 cross 1, because here number of filter is 50. So this one is the feature map, and the dimension, sorry, number of trainable parameter. So 3 cross 3 cross 3 cross 50. Okay, so that is 27 multiplied by 50. Yes. Clear? Okay, so here this is the convolution, this with respect to the one dimension data. Okay, so this, okay, so let me just explain this here in this lecture. Okay, so let me rub this part on. Okay, so now how do we perform the convolution operation in the one dimension data? So let's say, say the picture. So, okay, so learnable parameter. Yes. See, this input image is 5 cross 5 cross 3, and the filter, the dimension of the filter is 3 cross 3 cross 3. Okay, and here this number of filter is 50. Here the number of filter is 50. So if number of filter is equal to 1, the dimension of the feature map, that will be 3 cross 3 cross 1. Okay, and likewise we have the 50 number of filter. This one is a one single filter, and like this 3 cross 3 cross 3, that we have 50 number of filter. This is a one filter. This is a single filter, and with this single filter, the dimension of the feature map, that is 3 cross 3 cross 1. That is only one. Okay, and the number of filter, let's say in place of this one, let's say number of filter is 50. So the dimension of this feature map, that this is one, this one is a second, this one is a third, and up to that is 50. So that is 3 cross 3 cross 50. And trainable parameter, so 3 cross 3 cross 3, that is a one filter. This one is a one filter. And if we have the 50 number of filter, that is 3 cross 3 cross 50. So that is 27 cross 50. Now is it okay for you? Yes. So now it's 100 data points, and the that's 5 channel. Okay, number of channel, that is 5. Okay, correct. Now the filter size, let's say 3. Okay, so filter that is equal to 3. So filter is equal to 3. Now you tell me the dimension of this filter, this complete dimension of the filter. The filter is equal to 3. Now you tell me the dimension of the filter. It's a 3 cross 5 because the 5 channel are there. Okay, so 3 cross 5. So 3 cross 5, this one is a 3 cross 5. Yes, so that is a 3 cross 5. Okay, now tell me the dimension of the feature map. Dimension of the feature map. So 100 minus में 3 plus में 1. So 100 minus में 3 plus में 1, that is 98. So 98 cross 1, because number of filter is 1. Filter, that is filter size, that is equal to 3. Okay, and the number of filter, that is equal to 1. So that the feature map, the dimension of the feature map, that is 98 cross 1. If number of filter, okay, that are having the size equal to 3, so let's say number of filter, let's say 40. Okay, so in that way, so the dimension of the feature map, that would be 98 cross 40. Clear? 5 cross 1. So 5 cross 1. So see, 3 cross 5. Okay, that is the dimension of the filter. And this 98 cross 40, if 40 number of filters are there, so 98 cross 40, that is the dimension of the feature map. Okay, fine. So now we are having 5 to 6 minutes more in this session. Now let me take your questions regarding this CNN, this padding, pooling, stride. Okay, and in the next session that we will start the family of the CNN, Lanet, VGG, AlexNet. Yes. Is there any doubt? Okay. So dense layer. So this one is a yes. Dense layer is like is a this kind of this ANN, that is artificial neural network. This input layer, this hidden layer, that is output layer. Okay. So the input layer, that is a one dimension. Okay, one dimension. So this one is the feature map, or this is the output after this pooling. And let's say this one is a 6 cross 6. Okay, so now this we have to convert this in a 1D. So this one is a first row, this one is a second row, this one is a third row, fourth row, and fifth row, and sixth row. Okay, so let's say this one 6 cross 6. So that is 36 number of nodes in this first input layer of this fully connected part. So how to decide how many convolution and how many filters that will be applied? So how many number of convolution layers? So again, that it depends on the application. Okay, ResNet, that we will see. Okay, answer of this question in the second session. Okay, so how to decide how many convolution and that will be applied. Okay, clear? So in the LANet 5, this LSNet, okay, then VGG 16, VGG 19, okay. So it's a one conception is if you increase the number of layer, okay, then you extract the more features from the input image, okay. But in the ResNet that we will discuss in the second session, okay, if you increase the number of layer, okay, if you increase the number of layer, the performance that may not improve. Okay, the performance that may be worse if you increase the number of players. Global max mean average means, okay, see the yes. So global max pooling and global average pooling. So global max pooling, okay, it convert this whole image into a one scalar value. So better to use this global max pooling at the output side, okay, not in between. Global max pool and global average pooling. Global max pooling means that is this whole image, that is it convert into the maximum this value of the pixel. So maximum pixel value, that is 100. So that it convert this whole image in a one scalar value, that is 100. And global average pooling, again you have to add all the pixel value and divide by number of the pixel. Okay. So that will be global average pooling. So again, that output of this global average pooling, that is one scalar value. Okay. So question is, how much more resource intensive is image? So if you have the text based data, okay, so better to apply uh, RNN, okay, LSTM or GRU, okay, RCNN also, reason that convolution neural network. So RCNN, RNN, LSTM and GRU, gated recurrent unit. Okay, if you have the text based data. Yes. Any other question? Yes. So every epoch, the value, the pixel value that will update every epoch, that at the back propagation, okay, at the time of this back propagation, so that we need to update the value of this filter. Okay, these are ultimate weight. As you, if you compare this convolution operation with this artificial neural network, so now see here, this one is the input image, input layer, this one let's say that is hidden layer, and this one let's say that is output. So now a weight, that is 4 multiplied by 3, so that is a 12. Okay, if you consider the bias, that 12 plus by 3, that is a 15. So that is W0, W1 up to this W12, okay, W11 and 3 bias. Okay, so these are the weights. You need to update these weight, okay, at the time of the back propagation. So in the same way, you have to update the value of this pixel of this filter, okay, every time at the time of the back propagation. Yes. Any other doubt? So in the next session, that we will discuss the family of the CNN. Yes, is there any doubt? Okay, fine. Okay, thank you all. Okay, so now we are just wind up this session, and in the next session that we will meet at 5 o'clock.